we have Chandler Carruth doing the second part of his talk. So in case you forgot, let me just check if anything changed. Okay, Chandler is still the leader of Google's C++ platform and LLVM teams. And now for the second part of his talk, making C++ easier, faster and safer with tools. Let's welcome Chandler Carruth.
All right, thank you guys. Thank you everyone. This is fantastic. I'm glad to be back for the second part of this talk. Okay, I can barely see anything here, but I can't give up polling the audience. So I want to see how many hands, how many folks were in the first talk? Almost, oh, no, let me ask a better question. How many folks were not in the first talk? Okay, so some people. So just as a very, very brief sum up, all right, writing C++ is hard because you're trying to think about complexity and you're spending your time doing boring manual tasks. Computers are really good at boring manual tasks. We should teach computers how to do the boring manual tasks that you have to do in C++. We've done it. It's called Clang format, Clang tidy. Go search on your favorite search engine and find the awesome documentation. Read up all about them. Please use Clang format when you write your code. There, that's it. That's the entire first talk. You can laugh at all those people who sat through like an hour and a half talk for that. All right, so now we're going to talk about something completely different. We're going to talk about really how we extend from making things easy to making them safe, right? How do we just like go further than just writing code, but writing correct code? Because I know it's fun to write code, but I don't know about you. I like to actually write correct code. That's always seems relevant. And so we're going to focus on that. Tools for kind of debugging and protecting your code, how you can kind of accelerate this aspect of software development, because this is probably the other really big time sink for developers today. And all of this comes down to a very simple idea. We do not want the explosions, but sadly, the introduction was correct. I'm sure we'll have plenty of explosions during the course of the talk. Okay, so we need a plan. We need a plan for how we're going to tackle this, because like, how many folks here like think debugging is easy? Right. So that is fewer people than thought C++ was easy. So we have to be really careful when we attack this problem. We've got to think about it in a very structured way. And I'm going to share with you kind of the plan at Google for how to like attack this part of C++. Point one, we need to catch the common bugs, right? 80% or more, very early in the development cycle. Very low false positive rate, right? We need high quality, high reliability, immediately available feedback to programmers. Hey, you missed this. Really simple, okay? Turns out this is probably more than 80%. I always say the target is kind of 80% in the 80-20 rule, but this is incredibly important. Most of your bugs fall into this bucket. We then need to make testing an effective way to catch the long tail of bugs. How many folks here have written a test for a piece of software and then run it and the test passes and then they put it into production, they shipped it on a device somewhere and it turned out the software was still wrong. It just didn't happen to fail in the test. Anyone done that a few times? Right? So we have to be we can't just write tests. We have to write tests, but that's not enough. We need to make the tests much more effective at identifying the bugs in our software. Okay? This is how we find the subtle, complex bugs. This is how we go after the 20% of really hard to diagnose bugs. Next, we need to use fuzz testing, okay, to find all of the bugs we never thought to write a test for, that we never even had a way to write a test for. All right? This covers the bugs you didn't even think could be there, and fuzz testing helps find those. And finally, we need to use hardening to actually prevent exploits of the bugs that all three of these still managed to miss. There are always bugs. If anyone is particularly pedantic in the audience and likes the English language, we do not have fewer bugs. We have less bugs because bugs are not countable. Okay, right? You can't reach zero. They can't enumerate all of the bugs, but you can reduce kind of the kind of magnitude of the bugs you have to deal with. Okay, so this is our plan. We're not going to get all the way through this plan, but this is the plan. So let's look at how we actually do this. So step one, the compiler diagnostics are actually the first line of defense for your bugs. This is where we catch the 80% case overwhelmingly. It's in our compiler diagnostics. So let's look at that. Let's see if we can get some more explosions. All right, so In case you guys weren't in the first talk, right, all of this is live demo, right? I'm really going to be typing up here. If you can't see something, please shout. I can make anything larger. I'm happy to explain anything you see up here. Just let me know at any time. Let me get into some diagnostics. No, let me get into warnings. So in Clang, when we're doing C++ builds, the diagnostics that are trying to identify potential bugs in your code, as opposed to simple, invalid code because the C++ language says you can't write that, we call these warnings. And I have some examples here of a few warnings that I think are really insightful. So we're going to play a game. I like to play this game whenever I'm showing code on the screen and there are bugs involved. So I've got some code up here, and what you want to do is, as soon as you see the bug, you got to raise your hand. Okay, and everyone's like, oh, I can see this bug. This is easy. Okay, so now that everyone can see this bug, everyone sees this bug, right? Now I want to explain why this bug matters. It's because this code doesn't look like this. It looks something more like this, right? Can you see the bug? It becomes a lot harder, right? So fortunately, right, when you do this and you go and you ask the tool to see if there's a bug there, it just doesn't care. So let's see what Clang actually thinks of this particular code. Make sure we're using a nice modern version of the language. So you run Clang over this, and it's going to give you a warning, all right? And it doesn't care what line these things are on. It doesn't care how far away they are. It doesn't care how easily it can see the bug. It knows that there's a bug here, and it tells you every time. Okay, but this is, in fact, the easy case, right? This is not a scary thing. So let's look at some more interesting cases. All right, so how many folks see the bug here? Oh, well, that does make it hard to see the bug, doesn't it? Hold on. I need to remember from... Okay, how many folks can see the bug now? So don't feel bad if you're not putting your hand up. I wrote this code at Google on another project before I worked on a compiler. And I wrote this code, and I checked it in. My code reviewer reviewed the code, right? Thought it was good. We checked it in. We actually shipped it in a piece of software to every single developer at Google. And let me tell you, the cache did not do what we expected it to do. We actually brought down the production service because this cache didn't work effectively. So if I compile this thing, however, the compiler is very, very helpful. It tells me immediately that this is not doing what I want it to do. Unfortunately, 8 gigabytes requires more bits than I gave it. Now, I can almost hear everyone out there thinking, wait. It says long. That's a 64-bit type. Why is it saying I only have 32 bits? Well, this is where compiler warnings are really fantastic, because the compiler implements the exact language. It's not vague or kind of fuzzy. It's precise. It has to be. It's the definition of the language. And it knows that the rules of C++ say that this little expression here, this 8 shift left 30, is a very special expression. You see, 8 and 30 are literals, and the literals have a type integer, int. That's the type of the literals. And when you shift them, right, the result is still of type int, a 32-bit integer. It's only after the shift takes place that all of this is turned into a nice 64-bit value. And so that is exactly too late to get the correct behavior. All right, and so this is real code that actually shipped. I implemented the first version of this warning in Clang. Someone else ripped it out and did a better job of it later. But I actually implemented the first version of this warning in Clang because I felt so bad about having written this code and shipped it to so many people and causing so much pain. And it's a simple bug, right? This is trivial stuff. This is why I say you can't underestimate the value and impact of these 80% warnings. They come up all the time in so many places, and they're actually going to be the things that save you a lot of time and effort. Okay? Cool. So let's look at some more fun and exciting examples here. Okay, so this is fairly boring code. And this is kind of a classic piece of code that has a bug in it that, like, everyone is taught, no, you got to watch out for this bug. It'll catch you, right? But how many folks got taught about this bug in school, right? Yeah. I definitely was told, and despite being taught about it, we still make the mistake, because it's very easy to make this mistake. But if you hand it to the compiler doesn't care. It sees right through it. This is one of the first compiler-based kind of, really great bug-finding warnings. This is implemented in GCC just years and years and years and years ago, and it's just a fantastic warning. It's a fantastic example of the utility that compiler warnings can provide for you, okay? All right, so what are some more less common things, though? So this is kind of an interesting one. This is where things, in my opinion, get really interesting. How many folks spot this bug? This bug existed in Chrome. It existed in tons of projects in Google's code base. We were absolutely horrified when someone wrote this warning in Clang and we tried to turn it on and we discovered how much code broke. A lot of folks aren't putting their hands up. This is kind of annoying to see, right? It's really sneaky where this bug comes from. But if you ask the compiler, it tells you. You called memset and you did size of, but you took the size of the wrong thing, right? You took the size of the pointer you were passing in, not the actual struct it points to. And so this, on a 64-bit system, always initializes exactly 64 bytes, right? Now, if the pointer s, bits, yes. If the pointer s points to something smaller than that, you're going to have a kind of immediate bad time because you're going to write past the end of it. And maybe that's okay. Maybe alignment will save you. Maybe it will all be okay. What really gets me is when the type is actually much larger than that, which is the common case. Because when the type is larger than that, this won't always fail, right? Like, this will sometimes appear to work. Sometimes the memory was already zeroed. Sometimes only the first pointer needed to be zeroed. And so it could work, kind of, until it doesn't. And that's one of the great things about the compiler diagnostic. The compiler doesn't get tired of reading your code and get sloppy looking for this kind of bug. It's dedicated, right? It's reliable. It's always going to check, and it's always going to find this stuff. All right, so that's one of my favorite warnings of all time in Clang. All right, let's look at something even more tricky. So this one is another great bug from the trenches, as it were. A team came to us while we were working on Clang, and they complained about they had a bug in their production service, and it was crashing. And they were really upset because right before the thing crashed, it tried to log all of the important information for diagnosing the crash. But all of their logs stopped right before all of that important information. And they could not for the life of them understand why. They knew what it was crashing, where it was crashing, and it was after the log happened. They had done a special production push just to add this logging to try and figure out this crash, and yet it hadn't helped. Well, let's see what actually is going on here, because this one is, I never see this when I'm reading code, right? It looks correct. It looks completely correct. But if you ask the compiler, it's going to tell you a very sad story. So unfortunately, the ternary operator's precedence is not what you wanted for this particular formulation. Shift wins out here. And so we take this Boolean and we shift by it, which is really helpful, right? And then we have a ternary and then some junk off of the end of it. We even tell you that, like, by the way, like we weren't even able to use that thing you dropped on the floor there. Warnings like this can solve, tremendously complex problems for humans, even though this is actually a very simple bug in the code, right? A whole team lost a day's worth of debugging on this production crash because they did a specialized push that was just intended to add the logging, got it out into the wild only to find out it didn't log, right? And they lost a whole day, and they had a bunch of crashes continuing for a lot longer than was necessary. All right, so this is the kind of thing I mean when I say that this is your first line of defense, and it's incredibly important. All right, so I think that's all of the really fun examples we have here. But I think there's some other things we should talk about. So, we have one more fun example. Oh, this example. How many people see this bug? This is a terrible bug. Because it's another place where we implemented the warning expecting, oh no, this doesn't actually happen in real code. No way. No way does this actually happen. And we ran it over the code, and we're like, a couple of people have spotted it, right? We ran it over the code, and we found out that this people actually had this all over the place because it compiles. This code compiles, right? But man, that is not supposed to be a comma. right? That is just not supposed to be a comma right there. It's really clear what that is supposed to be, but the compiler, is required to accept it. And that's where warnings come in, right? We go and we tell you, no, this is actually related to the vexing parse. We're sorry, we don't like that we had to parse this bar as something other than a function call, right? That we had to parse it as a declaration. It's horrible, but we're required to do so. So we tell you, look, you didn't think this was going to be a function declaration, but it is. And we even go backwards and we find the comma. And we point out, like, by the way, you've got this comma. Are you sure you don't want a semicolon? And we actually implemented this warning, at first we actually implemented kind of the clever syntax here because we actually had the opposite bug in the source code. It was the other way around. The person had written this, and they were trying to initialize bar, and they just didn't realize that they were hitting the vexing parse. And we got a bug report because our error message for the vexing parse here wasn't awesome. And so we improved the warning, and then we ran it over more code, and we found all of these places where people just had commas at the end of lines and had no idea that that comma was actually not a semicolon because they trusted the compiler. All right, so this is all great and wonderful and stuff, but this is kind of very localized, very microscopic things, and we need to be able to extend our first line of defense past that. We need to be able to extend it to something that's a lot more complex. So I have to show you a little bit more code at this point. But I'm going to walk through it. We're going to try and put all this in order. All right, so here we have at the very top, we have a mutex, okay? And this is not really a good mutex type. I'm not advocating that this is an excellent API, but it fits on the screen here. And so we've got two very boring functions, lock and unlock, okay? We go and we build up an actual mutex. We build up some shared state here. So we've got a mutex m, and we've got an integer x, right? And m here is going to guard x. Okay, that makes sense, folks? So we should have guarded access here. Now we have a couple of functions, foo and bar, all right? And foo and bar also are supposed to be called underneath this mutex, with the mutex already held in a locked state, right? But unfortunately, there are no comments here, or if there were comments, the programmer didn't read them because, programmers are good at that. And so we have some complex code below this. Now, if anyone can actually spot the bug in this code, I am really impressed because this is just really annoying to spot the bug here. Say what? Well, okay. So maybe there's some unlocks missing, right? There's some problems here. But this is we've got complex control flow, right? We've got a loop, all kinds of, this is essentially a state machine interacting with mutexes, right? This is really subtle stuff. So we can't just solve this. We can't attack this with a very simple localized warning. We need something much more powerful to go after this kind of bug. And so we do something called model checking, or essentially annotated APIs, which give us a set of invariants that we know need to be preserved for a set of APIs. And so these are sort of hypothetical annotations that we might use, okay? So we want to say that this mutex is lockable, right? We want to say that it has a lock function and an unlock function. Now what this is doing is it's essentially mapping a high-level C++ API into a high-level kind of specification through annotation for what the semantics are of this API, right? There's this relationship between the type, the lock, and the unlock that all interact. And we're communicating that through annotations so that even if it's user code, if it's standard code, we can annotate them and we can get the same kind of basic semantic checking. We then come down and we annotate the actual variable to say x is guarded by this mutex. And so any access to x needs to be carefully placed under that mutex lock. And we continue to say that foo requires the mutex lock to be held, but bar does not. And now that we have these annotations, these are checked by the compiler. So you can't delete them, you can't refactor them away, right? They're actually going to be something the compiler can keep track of. If I change the name of the mutex, it's going to create an error here because we actually have a real reference to the mutex here. We type check it, we syntax check it. This actually is compiled code. And then we get to write, this normal looking code down below. So what does the compiler think about this? Well, you have to understand, sadly, it doesn't look quite that clean. We actually have to spell these annotations in a really annoying way right now with a bunch of underscores and attribute. But like, it's the same as what I just showed you, right? Same annotation scheme. And if we go and compile this code with a special warning, eventually, when my keyboard catches up to me, called thread safety, and this is essentially taking a particular set of semantic contracts and applying a check for them based on those annotations. And so it's going to actually give us a whole bunch of errors here, okay? First off, it's going to point out that we're reading this variable x while we're not holding the lock x, the lock m, right? We can spell out exactly what isn't being held, what's being read. We also know that we're calling this foo function, and that foo requires this mutex to be held. So we point out that bug. And then we can even point out the loop structure bug here, where we actually continue a loop, right? And when we continue the loop, we can figure out that the loop started with this mutex held, and we expect mutexes to be locked and unlocked in a symmetric pattern. And so we know that when you continue this loop without reacquiring the lock, that continue is itself going to be a bug. And we come down and we even tell you, by the way, here's where you locked it on entry into the loop, right? So this is really advanced control flow-based semantic checking of a particular API contract that programmers found problematic. Like locking and unlocking, lock safety and checking was something our programmers came to us and they said, this is a huge source of problems for us, right? We're spending tons of our time on it. And so we can build this annotation scheme, annotate the API, teach the compiler to check it, and this gets us a large class of bugs being caught very early in the development cycle. And it turns out there are a lot of interfaces which are very amenable to this kind of extremely high level and abstract semantic annotation that lets you check them. We've even started to get the first one of these standardized in C++ 17, which is the no discard annotation. And what that means is that you can't just discard the returned value. There's some semantic importance to that returned value. If it's returned, you have to use it. You have to be explicit with how you're going to use it. Okay? You can think about methods like empty for how this can be used. Questions about this? Because this is the more kind of complicated example of compiler analysis. I want to make sure everybody's happy. All right. So that's our first line of defense. But what about those really bad bugs, right? These are all, like, even with the kind of API semantic model checking, these are all still fairly superficial bugs. These aren't deep, subtle things. These aren't going to happen 1 in a million times. These are things that have pretty evident causes, okay? So how do we get those? Right? The bugs that actually cause things to go boom. So there are a bunch of tools that have been built over the years to attack these bugs, mostly around dynamic analysis of your program's execution. Two of the best known ones are Valgrind and Pin. Pin was built by Intel. Valgrind's kind of an open source project. But there hasn't really been a lot of adoption of these tools. They tend to stagnate. And one of the core reasons why we think is because these tools are unbelievably slow. If you take a program and you run it under Valgrind, you can expect a 10x to 20x performance hit, okay? If you run it under Pin, you can expect a 50x to 100x performance hit. And at that point, your program may not finish. You can't handle any interesting load. You can't run large tests through your software, and that makes it really hard to spot subtle bugs, right? These the same things that make the bugs subtle also make it hard to run under these constraints. So it really blocks their adoption. The other really nasty thing is that they actually miss a bunch of bugs. They're kind of weak approximations of the semantic model your program is executing under, because they're seeing the executable after the compiler and everything else is done, and they have to deal with the fact that that executable assumed a lot of things about a particular hardware platform or a particular operating system. And there's no way to catch any kind of bug due to portability or due to variations in machines. And the last big problem is they don't actually help you fix the problem. You get very confusing error messages from these tools. I don't know if you've used Valgrind, but it can be completely mysterious what is actually gone wrong when you get a Valgrind error report. And so we think that combined, that's just really blocking users from using these tools. So we built a new set of tools in LLVM called the LLVM sanitizers. And these are designed at the same set of problems, but they leverage something pretty new and exciting that makes them much more powerful. They are dynamic tools, but they're using compiler-driven instrumentation in order to be much more precise, much more efficient, and have very, very helpful error messages. So there are three primary sanitizers that you want to keep in mind: address sanitizer, thread sanitizer, and memory sanitizer. The reason that there are these three sanitizers is because they all have one thing in common that actually prevents you from doing two at the same time. They use a technique called shadow memory. Okay? For every piece of memory in your application, these tools allocate a corresponding chunk of memory at a very predictable offset in the address space, and they track metadata about the original memory in the shadow memory. But if you're doing that, you have a problem. If you want to track both the address sanitizer metadata and the memory sanitizer metadata, you start to run out of memory. If you add in the thread sanitizer metadata, you're completely out of memory. There's just no more space. And so in order to be efficient, we actually have to split apart the kinds of bugs that we want to tackle into separate tools. Okay? So there's actually a fourth sanitizer, but it doesn't share this property, and that's called the Undefined behavior sanitizer. This one's different in a lot of ways. So address, thread, and memory sanitizers are very much low-level constructs. They come in after the compiler has already optimized your code. They look at it after that, and they try and kind of analyze it for bugs and the fundamental requirements when that program is executing. These are very fundamental requirements. It's very efficient, and the bugs that they're chasing are incredibly hard. But Undefined behavior sanitizer is doing something different. It's jumping in before the compiler ever got its hands on your code. Okay? It's actually integrated into the language front end, and it instruments your code to point out language-level semantic violations very early on. Before they get optimized away or transformed into something scary that you didn't want, we put in checks at every step to try and prevent, some kind of undefined behavior from happening. And this lets you kind of check for both language-level semantics in addition to the fundamental execution semantics. Now, it happens that these language-level semantics are actually easier to check, and so Undefined behavior sanitizer doesn't require shadow memory, and you can combine it with any of the other three. And in fact, we typically do. We typically turn on some amount of the Undefined behavior sanitizer along with address, thread, or memory sanitizer. And it's often really nice to do that because it prevents you from getting a confusing report from one of these very low-level sanitizers that's actually about a bug that's a very high-level, simple semantic violation of the language. Okay, so I always mention these sanitizers, and I'm nervous about it because dynamic instrumentation is a very unusual kind of bug-finding tool. Unlike the static checks, if you don't have a test that actually exercises the part of your program with the bug in it, we can't find the bug. We have no way of seeing it. And so you have to have really good testing in order to use the sanitizers effectively. So I just want to emphasize this. This doesn't replace testing. This makes your tests much more powerful. All right, so let's walk through some of these bugs with, of course, more live demo. So the first sanitizer I want to look at is address sanitizer. This is easily the highest return on investment of all of the sanitizers. You will find so many bugs you won't know what to do with them with yourself when you run address sanitizer. So we're just going to look at a very simple example to give you kind of the flavor of what kind of bugs we see here. Unfortunately, because these are subtle bugs, all of my examples are now a whole lot more code. So bear with me. We'll try and step through it. So we have hello, and this is like the world's worst way to write hello world. Okay, sorry. But that's how we get a nice example. So we have this get hello. By the way, if you guys think you see the bug, right, like give a shout. That soon. So we have this get hello, which does this very elaborate computing of get hello. We have get world, same thing, more elaborate. And then we kind of use these to compute the pointers and stitch everything together. We've got a bunch of really awful pointer arithmetic here, right? Like, don't ever write code like this. But sadly, sometimes you have to deal with code that looks like this. And we want to find some way to actually check how this kind of violates the semantic contracts of kind of pointers in memory here. All right, so msan is different from address sanitizer. Address sanitizer is trying to figure out how you writing bugs that kind of violate the addressing rules, where you're walking off the end of a buffer, or you're using addresses after they've been freed or after they've been popped off the stack. Memory sanitizer is a bit different. It's actually trying to find bugs where you're actually using uninitialized memory in a way that isn't defined. All right, so yes, this one is at least working. So let's look at the code here. All right, so this is very simple, right? You can kind of see what's going on here. We have X. We didn't initialize X. We used X. And memory sanitizer is pointing this out, right? It says like you have this use of uninitialized value, right? It's in main, right? It tells you where it is. But this isn't a very helpful error message. So one of the things you can do with the sanitizers is you can add debugging information to try and get a more helpful error message out. So if we add -G to this and we run it again, we'll start to see a little bit more information. So now it's telling us exactly what line this is happening on, right? It's telling us exactly this location we have a use of uninitialized value. This still isn't the best error report. And so we have some options here that really help out getting better error report messages. Where's my command backup? So there's a special flag you can give to memory sanitizer. And this will actually give you a lot more information. It's unfortunately a lot slower, but often once you detect you have a bug, you can kind of narrow down the thing you're searching for. You can turn on a slower, more precise analysis. And so this is saying, look, we've got a use of an uninitialized value, tells you where it is, but it also tells you where that value came from without being initialized. Right? And so it says this an uninitialized value was created by an allocation, gives you the variable name, the stack, and the function it showed up in. Right? And this is a bug that like Valgrind can't always find, because Valgrind can't change how your stack works in every case. And so this is really, really powerful stuff. All right? Happy about this error messaging? I can come back and try and figure out why Asan doesn't work, but I want to get through at least some more sanitizers first. All right, so let's look at tsan. So tsan is called, or thread sanitizer, is looking for a very different kind of bug. Okay, so thread sanitizer, despite the word thread, it isn't sanitizing kind of thread safety in the normal sense of mutexes and other things. It's actually sanitizing the thing that happens when you have threads and causes the worst kinds of bugs, data races. Okay, any kind of racy access to data, to shared data. And it does this at a very low level. It does it using the same formal model for data races that the C++ memory model and standard uses to kind of define what is a correct C++ program. So let's look at some of the code that we have here. All right, so we have a bunch of code here, right? Unfortunately, in order to do this, I have to have quite a bit of code. So the first thing I have here is I have my bad shared pointer, right? Don't actually build your shared pointer this way. And this is going to have kind of an obvious bug in it when you get down here, because you're going to see that we have this shared state for the shared pointer that's keeping our reference count, right? We're incrementing it, right? We've even explained that. And we have this lovely comment that I really love. Increment is atomic on x86, right? And this is actually, technically speaking, true. The increment instruction is something you can make atomic on x86. But this is a really big assumption that's kind of been made in the code. This is what we see all over the place. We'll often see code that appears to be correct because it was relying on some assumptions of x86 or some other platform-specific thing, but in fact it doesn't. We also have, the decrement and the rest of this. We have kind of the rest of the core functionality. We have our boring little integer here for the shared state, and then we have some code to use this. And this is a real program. It will actually create a couple of threads, right? Get the values out of their smart pointers, join the threads. Nothing too fancy, right? And so even with this simple of a program, we should be able to actually test for this with thread sanitizer and see it working. Let's give this a spin. All right. So Thread Sanitizer prints out a lot more information because data races are really complex to explain. All right. And so at the very beginning, we already have kind of more information than we ever wanted. It says, hey, there's a data race. The very first thing that TSAN tells you, I really love, it tells you the size of the data race. Right. So there's a write of size 4 to memory that isn't properly synchronized. Right. Then we get the backtrace of exactly where this happened. And we can see, like right down here, way out, we see the line number in the column, right? It tells you exactly where the write took place. You can see where the thread got launched from in my main function. All of this information is there. And then you can see what it is that it actually was racing with. We can see that there was a previous write of size 4 to the same address, right? And this is, again, showing you, all the things. Here's where the Lambda is called, right? Here's where more parts of the Lambda implementation and threads implementation is called. All this coming out of kind of how the thread is implemented, right? That's why the stack ends in null, because this is one of the threads created by my std thread calls in main. We then give you even more information to help you debug this. We tell you where this location is in memory, right? The location is a heap block. We tell you where it's allocated, and this is really nice because it points us at the actual shared pointer, where we created the shared pointer and created its shared state on the heap. We can actually find, that's where this integer isn't, right? And then we continue to say where these threads came from. So if you don't, I didn't even expect there to be a thread accessing that state. This tells you how those threads came into existence. Lots and lots of debugging information here. Make sense? And you'll note that the program works, right? It works. And so you don't see this until something really complicated happens and it goes wrong, usually, in a serving system, right? And then it goes down, bad things ensue, right? But Thread Sanitizer can actually take a very formal look at your program and demonstrate that you failed to synchronize properly. One of my favorite warnings, well, let's see if I have it. Let's keep going. There's some more examples here for Thread Sanitizer. Thread Sanitizer is one of the most amazing inventions in computer science recently. All right, so let's look at this one. This one is wild. All right, so we have some code here. We have a structure, and it has bit fields in it. All right, so we've got some advanced stuff here, and these bit fields are 8-bit bit fields, so they're a whole byte. We're not talking about sub-byte access. And then we have some code that initializes the struct, and then we create a couple of threads, and on the threads we kind of examine the bit fields and then change their values in various ways. Right? And then we join the threads and we're done. Right? Pretty classic driver for my examples. But like bit fields, right? This can't be that. They're two separate variables. They're both bytes large, and so you might think that this is okay. Unfortunately, Thread Sanitizer is going to point out a bug here pretty quickly. So the issue here is that bit fields in C++ have a special set of rules. And it says that 2 bit fields that are adjacent are actually a single memory location, no matter how big they are. Okay? As long as the bit fields are adjacent, they're one big memory location. Until you have some 0-sized bit field, we keep adding more bits into a single memory location. And data races in C++ are defined in terms of memory locations. So it doesn't matter that this is a byte, or it could be 4 bytes, or it could be 8 bytes, or 20 bytes. That wouldn't matter. The key thing is that because we have these adjacent bit fields, we form one large memory location, and when we access it in this racing way, those actually turn into data races. Even though they don't seem like it, right? You might superficially think, but I'm just accessing 2 fields independently. It doesn't matter. They're going to be data races. And you can and TSAN's going to tell you about this. So it actually says, look, the read is of size 2 bytes, not 1 byte, even though you have only 1 byte fields. And that's because C++ says you read the entire memory location when you access a bit field. We give you the stack trace again, right? We say that the previous write was also size 2. And then we give you the location. We say, by the way, the location is on the stack. We know that that's where the location is. We tell you what function it is. It's in the, or what thread it's on, so you know what stack created this memory. And we give you where the threads were created from. Make sense? Right? Really, really cool. All right, you guys are just not buying all of the awesomeness of this. So let's dial it up a little bit here. This bug is just demonic. Okay. So we've got more synchronization here. I've got condition variables. This is a fun example. All right, so we have a class A. All right, class A has a virtual function f, which is pure. So this is an interface A. Has a non-virtual function done, which calls f, and it has your expected virtual destructor. Within A, we have a mutex, a condition variable, and an isDone flag. Okay, and the mutex is guarding the isDone flag. The condition variable is signaling when something changes to wake up a thread, and we can see kind of how this works. If someone calls, and this is calls done, right? Then we call f. We do the virtual dispatch into f, and then we lock the mutex. We set that this is now done. We notify the condition variable, and we print out, hey, by the way, someone called done, and we return. And when we return, we release the lock. Now in the destructor, right, we acquire the lock first. We then say, hey, we're waiting for done, right? We're not going to touch anything until someone actually calls done. So we wait on the condition variable, right? As soon as the condition variable is available, we acquire the lock. We check whether it's done. If it is, then we destroy the object, okay? This allows us to kind of write code that looks something like this. I mean, we have to override f for class B here, and then we can write something like this. So we create an object of type B, right? This empty f implementation that doesn't do anything. We create a thread where we do f, and then we call done, and then on the other thread, we delete the object, right? And all of the state here, right, is synchronized with a mutex. So how can this possibly be a data race, right? I will say, every single data member is accessed under a mutex. This passes all of the mutex checking code. There's nothing like that there, right? And yet this has a data race in it. So this is an exciting data race because it's a data race that the programmer didn't directly author. So if we compile this one under tsan and run it, it will tell us all about this problem. We have a data race on the v pointer inside of the class. Okay? It's a member you couldn't even see, but we managed to write code that has a race on it, which is terrifying. I mean, you should be terrified about this. Right? So let's just go back to the code briefly, because there's enough code here. I feel like you need to kind of keep both in your head. So we have these virtual functions in A, all right? And that means we're going to have a virtual table to dispatch through them and a v pointer inside the object to store the address of that virtual table. That's a particular ABI. And then B gives us an implementation of these, and it adds another virtual table, right? And now the v pointer can point to one or the other virtual table. Now the important thing here is that B's destructor doesn't do anything. And so when you delete an object of type B, right? And we do that down here, right? So when we delete this object here, right? We call B's destructor doesn't do anything, and then we call A's destructor. But in order to call A's constructor, we first have to destroy the outer B object and make this an actual A object again. And so when you call A's destructor, the first thing it does, because it's a base class, it sets the v pointer to point to A's virtual table. And it doesn't do that atomically, right? That's just a flat out race condition. And so while one thread is calling virtual functions on this object, the other thread is setting its v pointer to point to the sub-object's virtual table. With me? All right? Now here's where it gets really scary, because I can come up here and fix this. And I don't know if they've actually hidden this or not, but this is actually a bit worse. When we first found this bug, we were really, really concerned, because when we first found this bug, it even happened in places where we kind of thought it shouldn't. So what if I do this? Right? What if I actually check in B before B is destroyed that all of this is okay? Does anyone think this is going to fix the bug? Like, I mean, I understand I can't compile this because it's done as private and stuff. But like, does anyone think this is going to fix the bug? It won't. And it won't for a really surprising reason. You see, because your class could be a subobject of some other class, the ABI says that as you start your destructor, the first thing the destructor does is it sets its v pointer to its current v table. Does not matter what the v pointer is already, it sets it to the v table. Okay? And so the very first thing that any virtual destructor will do is write to the v table, and that can cause a data race immediately. We actually have tried to hide this for kind of final objects because you're actually writing the same value to the vtable as is already there, which is particularly not scary in any kind of synchronization context. And we can omit that write in a way that is actually completely correct. But yeah, right now this is just really annoying that like the ABI makes it very challenging to call destructors from multiple threads and then synchronize inside the destructor. Right? You essentially can't write it as a thread-safe thing because of these virtual table v-pointer writes. And this is why TSAN has a dedicated error message just for races on the v-pointer, because it's so surprising and confusing. And it tells you all about where these writes and reads are, where the object is located, where the threads are started, just like everything else. Okay? And so here Thread Sanitizer is actually telling you about an incredibly subtle bug that you don't even see in your code that can only happen because of the kind of odd rules the language imposes on you and with the particular implementation. So this is what I mean when I say like the long tail of incredibly subtle bugs. All right? Folks happy about this? All right, so Asan prints out something that looks like this. And this is just classic Asan report. So here, let me go back and look at the code, because we didn't actually look at this version of the code. So this is a less crazy hello and world implementation. So we have this main function, which has this buffer it's going to try and populate with hello world, all right? And then it has a pointer, and then we do very C programming-like things. We copy, hello into the buffer. And if you look up at this one, we have some hello global up here, right? So we have hello and world as globals. So we first copy hello into the buffer, and then we copy, world into the buffer. Really, really boring, right? But, I'm bad at arithmetic, and so this doesn't actually do what I want. I mean, we can sit here and do the arithmetic, but the tools have done it for us. And so they point out that, no, when you're writing these characters in, you actually have a bug. Copy world walks past the end of the array, because I haven't taken into account null termination, okay? And so I've only got enough space for the actual characters, hello space and world, not for hello space world and a null terminator. And this catches it, tells you what line it happens in, tells you that it happened in main. Address sanitizer, because this tends to find the largest number of bugs in people's software, not the most subtle, but the largest number, we spend a tremendous amount of time making these error messages better. And so we tell you that this address is located in a particular stack of a particular thread at what offset. We then point at the stack frame from the function. We actually extract the entire stack frame, and we show you, right, you had this buffer in your stack, right? That's what's at offset 43, and that's what we're writing one past the end of. So you even know exactly which local variable it is you have to go and update. Make sense? All right, so that's address sanitizer. It even goes on. So it even shows you, I mentioned address sanitizer uses shadow memory, right? It actually shows you the shadow memory so you can understand some of how it's diagnosing stuff. And so these red markers here, right? So we have this red stuff here and more red stuff here. Those are essentially called red zones. We're essentially padding out each entry on your stack with little regions that we can mark in the shadow memory as, not accessible memory. So that if you try and walk past the end or before the beginning of something on the stack, we actually flag that. And you can kind of see what the stack looks like here. You can see each of the three entries, right? We have buffer followed by a temporary and another temporary, and you can see this not red memory, so that's the valid memory, is buffer, right? And then we have another not red entry, which is for the temporary, and then the other temporary, right? You can see all of this detail from the shadow memory. This is actually how address sanitizer is actually finding the bug in your code as well. All right, let's look at maybe one more address sanitizer example since I have my backups. Okay, so this is essentially trying to fix the issue, right? And so we're going to try and make this work again, but we're still going to get it wrong. I suspect. But we should ask address sanitizer whether we get this wrong still. So let's recompile everything. Yes, we still get this wrong. So what we've done, so first off, in case people missed what we did here, is we moved it to the heap because we're like, okay, maybe stack memory is just hard to use correctly. So let's use heap memory, right? But I just wanted to show you kind of the different ways it diagnoses these issues. And here, in fact, it doesn't care. It's going to keep diagnosing it on the heap. But now instead of it being a stack buffer overflow, it's going to be a heap buffer overflow. It's going to tell you all the same information. It can't tell you about the stack frame and the variables within it because now there isn't a stack frame with variables, right? It's just some random heap allocation that you messed up. So we have a little less information to offer, but we try and give it to you. You can also see the shadow memory around the heap allocation. It looks a bit different because there's not these other entries on your stack, right? That's all that's going on there. So these heap errors are what Valgrind traditionally can catch and does a very good job of catching. But when it's on the stack, Valgrind cannot catch it because Valgrind does not know where one variable starts and the other and ends, and the next variable starts and ends on your stack. It has no way of knowing that. Address sanitizer has unique information here because it's compiler instrumentation based, and so it actually inserts this padding, those shadow regions, in order to find that information. Make sense? All right, so that's Asan. Really briefly, I want to show you some of Ubsan, and then I want to move on to some other stuff because there's still more stuff that we need to look at here. I actually have more live demo than I have time for today. All right, so we have bugs that are just language semantic bugs, really classic ones, right? Like signed integer arithmetic, right? Overflowing signed integer arithmetic, right, is not allowed by C++. If you actually do it dynamically, right, it's actually undefined behavior then, and then the optimizer gets to do stuff to it, but we can catch it by building with Ubsan. So if I go and compile this code, I mean, we even get a warning here because this one's really obvious. But just so you can kind of see what these reports look like when you see them from your code, if you run the program, we just give you a really immediate error message because there's not this subtle interaction of different threads or allocations. We don't have to work so hard to explain it to you. These errors actually tend to be really simple. It's just that we can't detect them until we run the program and see it. And so they look more like Klang's error messages, but produced dynamically when we run it. But we can do slightly more interesting things here. So let's look at another bug here. So this one is one I like. So this one is a little bit tricky. You're actually shifting a bit off the top of a value, okay? And this is actually also signed integer overflow according to C++. And it's particularly hard to see because it can kind of build up over time. It's not always really immediately visible. So we have at least a warning here to kind of let you in because these are all constants. And if you run it, we give you the same thing. We give you a nice runtime error saying, hey, look, you're not allowed to do this, right? So what else do we have here? Because this one is kind of fun. This one actually is probably one of the most prominent and one of the most important undefined behavior sanitizer bugs we have. This is really simple, right? So clearly, for some reason, you can't do this, but it's not really obvious when people look at their code this is a bug. It turns out that the max value of an int, if you put it into a floating point number, we round off some digits. If you bring it back into an int, those digits are now gone. And so this does not round trip cleanly. And people don't seem to expect this. And the worst part about this is how many bits it rounds off isn't well defined. Like, it's not like some nice predictable amount of rounding. Because these things don't fit within the dynamic range, it's actually just flat out undefined behavior, and you really, really, really get the wrong thing, right? So we first convert it to a float. That's defined, but there's a rounding error, and unfortunately the rounding goes in the wrong direction. And then we have to come back from a float to an int, and when we do that, we actually cause signed integer overflow, because the float doesn't actually fit in the integer. Right? And so people don't realize that this is going to trigger undefined behavior. And if you actually evaluate this, right, if you just tell the compiler to go away and let you do this, right, and you turn off all the optimizations, if you somehow tried to make this okay, you still wouldn't be saved because we actually observe different integer values coming back on different hardware. Okay, we actually get a different result on different hardware when you do this. And so, for example, this is a place where you can observe the difference between PowerPC and x86. And so having these kinds of checks is incredibly important for portability. We've actually turned on this particular check on an incredibly large amount of Google's code in order to get better portability across architectures. Right? And so that's a case where like it might always do what you expected, even if it was a silly thing, until you port it to some other architecture. Let's see if there's any more of these that are super interesting. I think we may be running low on interesting UBSAN bugs here. But let's at least look at this one. This one is I really like. So this code, if you were to just turn off all of C++'s semantics, which is kind of hard because then you don't know what the program means, but like setting that aside momentarily, right? There's undefined behavior here because we're binding a reference to a null pointer, okay? And you're not allowed to do that in C++. But we then turn it back into a pointer, and then we check the address to see if it's not null, okay? And so if you didn't have this rule in C++, the code will execute, and it will not ever do anything with this null pointer. So if you actually try to dereference a null pointer, right, you get a seg fault. If you run it with asan, asan says you can't dereference a null pointer. But this won't ever dereference a null pointer. Whatever it ends up doing, it won't do that. And so it's hard to actually check this kind of thing if you don't actually have your hands in the front end, in the compiler itself, to say, no, the language says you can't bind this reference even though you're not reading from the memory when you do it. And that's really powerful. And so here we can compile with sanitizer on. And it tells us reference binding to a null pointer, you know, and that's the nature of the error. And it's really nice to be able to lift errors up to this very high semantic level. All right, so let's look at let's go back to our slides briefly because we've talked a lot about like the sanitizers that are available and what they can do. But you have to remember they can't do anything if you didn't have a program that you could run that triggered that behavior, right? You have to have a program you run that triggers that behavior before they can do anything at all. And so they're only as good as your tests. So you test everything, right? Everything. There's no case that you missed when you were testing your code. Surely not. Well, sometimes you do. Sometimes you miss things. Anyone familiar with this logo? Heartbleed, okay? The OpenSSL authors thought they were testing things, right? We'd been running OpenSSL under sanitizers forever, right? We thought we were testing things. And yet, some crafty person comes along and points out that if you just send the right byte stream to this one part of the OpenSSL protocol, you can cause it to read arbitrary amounts of memory and send them back over the wire, which is really scary for an encryption algorithm. Okay, so we need some way to handle this problem, and the sanitizers alone don't cut it. Okay, so we need some way of doing this. How many folks think I can find Heartbleed while I'm up here? No faith. Okay, so I don't know what the bug is for Heartbleed. I don't know anything about OpenSSL, but I think I can find it. So let's do something real. We've been looking at toy code too much. Let's do something really real. So I'm going to try and find Heartbleed through fuzz testing, okay? So I have OpenSSL 1.0.1f, right? And what I need to do here is I need to build a pile of software. So let's look at the code first, and this will kind of explain what software pile we're building. So this is a piece of code, which is using OpenSSL. It essentially initializes OpenSSL, sets everything up, reads in some certificates, right? And then we have this delightful function called LLVM fuzz test1 input. And what this is going to do is it's going to take some arbitrary byte stream, and it's going to package it up and run it through the OpenSSL API here. Notably, it's going to do handshake, okay? And the idea is that this should like exercise all of OpenSSL's protocol that's behind this API, right? And if we can use, how many folks here are familiar with fuzz testing at all? Only a few. So okay, so backing up. Fuzz testing is this idea of randomly exploring the space to try to find bugs you don't know about, with test cases you don't even know how to write. Okay, so you try and reduce whatever API or whatever system you have down to have some very simple input, like a byte stream. And then you just randomly permute bytes to see if you can guess a sequence of bytes that will actually uncover a bug. Okay? Now, this has been known for years and years, decades. Okay, this is an old technique. But it never worked very well, and it didn't work very well because of one reason. And so what we're going to try and do is we're going to try and apply this old technique that doesn't work very well and see if we can make it work well. So we've got our fuzz test here. And we just have to somehow magically guess the heartbleed attack in that data stream, right? That's what we're trying to pull off here. Okay, so how do we randomly guess that? Well, the first thing we need is I'm going to need to pull something I prepared earlier. So I'm going to pull a version of OpenSSL that I built earlier, because we're running a little bit shy on time here, and a version of the LLVM fuzzer that I built earlier. Okay, so here we have two things. We have libfuzzer.a, which is the LLVM fuzzer, and if you go and search for documentation, it's very easy to build. And we have OpenSSL 1.0.1f, which I built earlier with all kinds of good sanitizer stuff. And somewhere I will find my command. There we go. Okay. And so here we have to run this monolithic command. I need flags first. All kinds of flags, sadly. So you have to pass a bunch of compiler flags to Clang in order to use this, because what we want to do is we want to essentially see if we can find a way to use the crazy sanitizer stuff to make fuzz testing more effective. In particular, can we just find these kinds of bugs more rapidly and more reliably? Okay, so this should build for me. Let's hope everything working correctly. Okay, so we're going to, I don't have any canned inputs here, right? I have you can see everything I've got here. I've got a server key and the signed bits. I don't have any bytes that conform to the handshake protocol at all. All right, and I didn't write any code that made them conform to the handshake protocol in this fuzz test. But if I run this with a bunch of cores, it's found Heartbleed. So that's how long it took to found Heartbleed. It's found a bunch of other bugs as well. Here we go. Okay, so we scroll up through all this scroll, we'll find this report up here that's really, really scary. So what it's doing is it's doing this kind of fuzz testing to try and find a bug. Here we are. And there is Heartbleed. So heap buffer overflow inside of TLS process heartbeat, okay, where we were able to just read arbitrary amounts of memory out of your SSL address space, okay? I didn't write anything about SSL here. I just took the API and I fuzzed it. Now, what makes this different from just randomly guessing byte strings? Well, it's the same thing that makes the sanitizers different from Valgrind in a lot of ways. Because we're part of the compiler, we can actually go in and change the code to make fuzz testing much more effective, right? The way you select these random byte sequences is the key. And we need some way of selecting the right random permutations to these byte streams. What we do is we actually collect the coverage information from the program that we're fuzz testing. So when we compile it, we instrument it to collect coverage information. We take that coverage information and we analyze each run over the program with any byte input to try and figure out how much of your program was covered. And that becomes our fitness function for a genetic evolver, right? We just do classic genetic evolution of the byte input stream, where what we try to do is maximize the amount of software that byte string covers. All right? That's it. You take that, and then you take the sanitizers to turn a non-deterministic bug into a deterministic crash. You combine them, and all of a sudden, fuzz testing works. It works in really powerful ways. We can start with no knowledge of a protocol, discover a conforming byte sequence to use that protocol, use it, and then find an exploit within it. The folks who've been working on fuzzing have been able to do things like construct conforming JPEG images from nothing by just looking at the coverage of the JPEG parser with random data coming in and doing a fitness function to evolve towards more code in the JPEG parser. It's incredibly powerful. It can find heartbleed in seconds with no knowledge of what it is or where it is, right? This is in the heartbeat stuff. We didn't even call that. We called these other functions in the SSL library, right? If you just take your API surface and you fuzz it, you'll actually explore and find all of these kinds of bugs. It's absolutely incredibly powerful. It's found hundreds and hundreds and hundreds of critical bugs throughout every piece of software in the world today. If you're writing security-sensitive software and you're not using coverage-directed fuzz testing, like you're really running a huge risk. All right, so that's the last of my tools. Let's sum up quickly. Right, complexity is the big challenge. Right, tools are what we can use to help us with that. We need to automate and accelerate all of these kind of boring and mechanical and redundant and draining things so that you can focus on the really hard problems of figuring out how to manage the software that you're actually writing, how to engineer it well, okay? You want to find bugs faster, 80% of them offline, statically, immediately in your build, right? You get the dynamic analysis to get this long tail of subtle, complex bugs that you would never catch any other way, right? You want to fuzz test so that you're actually sure to find the bugs before the bad guys that you didn't even think to test for, right? And so now you can get back to writing code and engineering software. All right. I also want to say thank you to all the LLVM folks. Like I said, all of this stuff is stuff that I have not personally worked on. There are an amazing crew of people behind all of these things. There's amazing documentation on the Clang and LLVM web pages you should go check out if you want to learn more. I have to give a shout out to all the people who did the hard work here. I'm just up here kind of advertising for them. And then with that, I'm done.
Can you briefly explain how does the thread sanitizer work? And my guess is that it tries all possible interleavings of your program, but this is probably time-consuming operation. So
yes.
I'm not sure if it's...
Okay, so the question is, how does thread sanitizer even work? And why is it not unbelievably slow? So first, I'll go in reverse order. You have to understand how slow these things are. They aren't fast. They are slow, but they're much less slow than the comparable tools. So thread sanitizer tends to be between 5 and 10x slower than your original application. It's the slowest of all of these tools. And the thread sanitizer analog that was built in Valgrind was between 50 and 500 times slower. So it still is a really remarkable improvement from the next best example we're aware of. Now, what it's doing is much more powerful than trying all possible orderings. I mean, if you try all possible orderings, you will find everything, but you'll also never finish. It's combinatorial. It's insane. You can't go very far. And so a lot of tools try to explore a small space of the permutations, but you have a lot of false positives, false negatives if you do that. You miss a lot of bugs. So what thread sanitizer is doing is every time you modify memory, it actually is keeping a log of all synchronizations which have happened before that modification, okay? And then it continues this log past the modification, and when you write to it, or when you read from it, it looks back across this log of synchronizations, and it says, hold on, did this read actually have a synchronization edge from that write? And if it does, then C++ says, it's not a data race. And if there's not an explicit synchronization edge, then it's a data race. This lets it find a bunch of things that aren't even observable data races in practice, but are in theory, and can lead to kind of latent bugs that become real later. For example, it will sometimes say, you have a race between these two, this write and this read. The race was synchronized by this call to sleep, right? And it knows that, even though that sleep waited long enough, because it slept for 10 minutes, that it doesn't actually synchronize anything. And anything that perturbs that sleep would immediately cause the bug to show back up.
So the follow-up question is, does it mean that it will find bugs for sure? That if I have a bug in my program, does it guarantee that it will find it?
It is not. So the question is, does this mean it has a hard guarantee? Not quite. So the log of synchronization events is finite. And so it is possible that the synchronization that you needed to see is there are too many events in the buffer and it can't keep track of them. And there are a couple of other very, very rare edge cases that it can miss, but it's extraordinarily rare. We don't know of any really interesting false positives where it says there's a race, but there actually isn't. There are some false negatives, but they tend to be much more rare than with permutation-based approaches.
Hi, so I have a question about address sanitizer. First of all, it's awesome and I've been a long-time user. And I noticed it has some shortcomings. Mainly when you have a structure and it has padding inside of it. When I first started using address sanitizer, it could not detect the invalid access to inside the padding of a structure. And the other part of this question is, how do you compare address sanitizer to Intel's MPX? Because I know that MPX is capable of detecting the padding access.
Okay, so there are two parts to that question. One is, how does address sanitizer compare to MPX? And the other one is, how does it handle internal to a structure overflows and that kind of thing? So internal to a structure overflows are very challenging because in order to do what we do with the stack, where we insert these red zones that allow us to observe overflows, we would break the ABI. And there's actually some flags in address sanitizer you can use, which will cause it to exactly that. It will actually pad out fields and structures, and it will try to do so only for structures which don't go through essentially C APIs. It'll try and make it work. And we've never gotten the kind of API compatibility story good enough to really deploy it widely. It's one of the things that remains a big open question for us. MPX is actually a really problematic thing. I don't want to give you a detailed answer there. Kostya Serbenya, who invented address sanitizer, has a public write-up on the address sanitizer wiki pages about MPX and why it doesn't work. It's not useful for finding bugs.
Okay, thank you.
It's a long story, but he has a good write-up.
Any other questions?
Is it possible that I run thread sanitizer twice and I get different results?
Is it possible that you run thread sanitizer twice and get different results?
Let's say that my program is reasonably deterministic by itself.
This is absolutely possible. It's even very likely. So if you're looking for a race, right, most races are non-deterministic, right, like by their nature. And so it's very likely that you have multiple threads and there might be multiple races and which one you encounter first dynamically changes.
Okay, thanks.
Yeah, I have a question about these annotations. You add two mutexes to find out if a variable is guarded by a given mutex, but can we actually detect logs, not logs, but when you have clash in the code, when you cannot progress further?
Deadlocks?
Yeah.
Absolutely. In fact, thread sanitizer has some deadlock detection in it. It's also possible to do deadlock detection in the library as well. I don't think that either of the standard libraries have a deadlock detection built into their mutex implementation, but we've actually talked about adding one to libc++, where in debug modes it would actually keep essentially like lock mappings on the side and look for cycles, which would indicate a deadlock.
I have a question a bit out of the box. You are working on future of C++, right? And okay, there are many nice features upcoming, but I have a question about basic stuff. Is there an idea to make standard algorithm functions take containers instead of vectors?
So the question is, are we going to update the standard algorithms to operate directly on containers instead of iterators? And this is completely unrelated to some of the things I've talked about, which is fine. Yes, there's lots of talk about that. Probably the most prominent and most recent work on that is the proposed ranges technical specification. If you search on the internet for ranges TS and C++, you'll find all kinds of information about it.
Thank you.
So I'm not sure if this is still a thing, but I noticed perhaps a year and a half ago, a notice about possible implementation of performance sanitizer. Is this still pursued?
So the question is, are we looking at some kind of sanitizer for performance issues? Yes. So it's currently called the efficiency sanitizer, and there's discussions and work happening in the open source project. I believe they have some kind of early stage prototypes in place that can do some amount of cache, like false sharing detection, and a few other tricks. It's not. It's still very early stages. I think they've just gotten started. If this is a place that interests you a lot, it's also a great place to kind of dive in and contribute and help out.
Okay, thank you.
And all this stuff is open source, folks. So if you ever want to write patches, right, you should send patches to it. It's all open source.
Big thank you to Chandler Carruth